We're going to talk about the electromagnetic spectrum in this video and do some problems relating to that. So right now, you might think, wow, how did we go from atoms to now talking about like light and the electromagnetic spectrum? But by the second part of these notes in the second video, you'll see how we tie this back in with atoms and electrons. So right now, we're going to talk about light here. Newton was studying light, and this helped lead to the quantum mechanical model of the atom. We know that light exhibits wave-like properties, so there's a little bit of physics here, and so there's some terms you need to know about. Whenever we talk about the amplitude, we're talking about the height of a wave, all right, and we'll look at this on a picture here. Wavelength is talking about the distance between two waves, and because this is a distance, we use meter for this. So this is going to be recorded in meters. So when we're doing the problems, the wavelength must be in meters. Frequency is basically the repeating over time. So it's basically the number of wave cycles to pass over a point. So it's basically how often something repeats itself. So we're using the unit hertz. So we have a new unit here. Hertz is the same thing as seconds to the -1 or 1 over a second. So if we're doing frequency in these problems, you need to be in hertz. You do need to know the constant here, c, which is the speed of light. All light in a vacuum moves at 3 times 10 to the 8th meters per second. So anytime you hear c, the speed of light, you need to know that that's 3 times 10 to the 8th meters per second here. We want to be able to understand the parts of the wave here, so I'm going to do a quick drawing. If you were to look at a wave, you would see here kind of like what you would expect, goes up, down, and then back up, down, so on. All right, so you're labeling your parts here. The amplitude is the height of the wave, so this distance here, the height of the wave to the peak from the baseline, that would be your amplitude. The distance between the peaks, so say from here to here, that would be your wavelength. Remember, that's going to be in meters. And then frequency is a little bit harder to show here, but basically it's how often the wave repeats itself. So if this wave was starting here, all right, it goes up and comes back down, but it didn't start to repeat itself yet because now it's going below the baseline and then back up. When it gets to this point here, that's when you see it start to repeat itself. So it goes up, comes back down, and so on. So the frequency for this wave would be from here to here. All right, so that's a little bit tougher to show, but your units of frequency are going to be hertz. And I just want you to see here the difference in wavelength sizes. So if we look at another wave here, take a look at the difference here. What if we had a wave moving like this? All right, notice the distance here between the peaks is much shorter. All right, so the distance here on the right has a much smaller wavelength, but then on the left, the wavelength is much greater. So when you have a higher wavelength or a greater distance between the waves, your frequency is smaller. All right, it takes a lot longer to repeat itself when the wavelength is bigger. And then when the wavelength is smaller, the frequency is much greater. It repeats much faster. So there's this inverse relationship between wavelength and frequency. So that's important. If you have a bigger wavelength, you have a smaller frequency. If you have a shorter wavelength, you have a much faster frequency here. So definitely understand at least those parts of the wave. The electromagnetic spectrum has 7 regions, and they're all ranked with respect to their wavelengths. And we just talked about this on the previous slide, that there's this inverse relationship here between wavelength and frequency. So you just need to know that as one goes up, the other goes down. So we have an equation here to explain this, all right? The equation we use for this is C equals wavelength times frequency. C we already know is the speed of light. You need to know it. It's 3 times 10 to the 8th meters per second. This symbol here represents wavelength. It must be in meters in this equation. If it's not in meters, you might have to convert it. All right, you got to get it to meters here. And then this V, it's not actually a V, it's actually a Greek letter, is representing frequency, and that's got to be in hertz. So for today, you're only going to have one equation to worry about, and you just need to be able to plug in and solve for one of the unknowns. But you need to know the speed of light is 3 times 10 to the 8th meters per second. You need to be able to recognize this equation, know this is wavelength, this is frequency, and what the unit of each should be. This is the electromagnetic spectrum here. And the good news is you don't need to know the entire thing. As long as you kind of know the ends and the visible light region and the relationships here between energy, wavelength, and frequency, you'll be pretty good. All right. So radio waves are down here on the left, and then gamma rays are going to be all the way down here on the right with your visible light in the middle. If you kind of have an idea of where those three regions are located, you're pretty good here. So now when you think about the relationships here, all right, radio waves, they're all over. You're being exposed to radio waves every day. So in terms of how safe are radio waves, they're pretty safe. All right. So if they're hitting you every day, the energy for the radio waves is very low. All right. So anytime you have a low energy, you're going to have a low frequency. So energy and frequency are proportional to each other. If you have a low energy, you have a low frequency. But then wavelength is always the opposite. Wavelength's always inverse. So if you have a low energy, low frequency, wavelength's always bigger. All right. But then gamma rays are like a nuclear blast. So think about that. If you got hit with a gamma ray, it's going to cause death. So the energy is very, very high. Therefore, it has a high frequency because frequency and energy are proportional, and wavelength's opposite. So it's going to be very small. So when you're looking at the visible light region, the visible light region follows a specific pattern. If you remember Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. All right, so Roy G. Biv here. And the easiest way to remember this is red, all right, is closer to the radio end. They both start with R. And the violet is closer to the gamma end. So in terms of energy, frequency, and wavelength here, since red is closer to radio, red would be lower energy, lower frequency, and then bigger wavelength. And the violet would be high energy, high frequency, smaller wavelength. So as long as you kind of know the ends here and the ends of the visible light region, you could kind of figure out anything that I would ask you about this. So you definitely need to know here energy and frequency are proportional, and wavelength is always the oddball. This picture is really good because it shows this in terms of the energy and the wavelength and the frequency. So we already said radio waves are pretty safe. You're being hit with them all the time. So if you notice here, if you look, it's kind of like the wave is out taking its grand old time, moving pretty slow. So it would have a very low energy. And if something has a low energy, it's proportional to frequency. It repeats very low or very slow. So you can see it's kind of like taking its grand old time. But then if the frequency and energy are low, the wavelength is much bigger. Notice the distance here between the waves. Now compare this to gamma rays. As you see down here, those wavelengths are so close together. The energy of a gamma ray is so great. The frequency is also great. So they repeat much faster. But then because of that, look at the distance between the waves. It's very, very small. Remember, wavelength is always the opposite. All right, and then you can apply that to your visible light region. The red is closer to the radio waves, so it's going to be lower in energy. And then the violet is closer to the gamma rays, so it's going to be higher in energy. In terms of this visible light spectrum, that's the only part of the electromagnetic spectrum that you can see, and you can only see a part of it. It's the Roy G. Biv. Visible light is an example of a continuous spectrum, which basically means that there's no gaps, there's no lines or bands. It just kind of blends one color right into the next, and it goes from red, which would be the longer wavelength, therefore the lower frequency, lower in energy, and violet, which would be the shorter wavelength, therefore which would be the higher frequency, higher energy. So you definitely need to know about the uh, energy, frequency, and wavelength for the red and violet regions. Now we're ready to try a problem here. This example says, what is the wavelength of radiation with a frequency of 1.5 times 10 to the 13th hertz? So for now, we only have one equation to worry about. It's just C equals wavelength times frequency. You definitely need to know the equation. You need to know what each of the letters means and what units they should be in. So it looks like here, remember, you're going to know two of the three, and there's going to be one unknown that you're going to solve for. So according to this problem, they're asking us what is the wavelength. So we're going to be solving for this. We're going to be solving for the wavelength. So that means we just plug in, solve for our unknown. So C, remember C is the speed of light. It's always 3 times 10 to the 8th meters per second. It's a constant. It's always that number. Equals wavelength, which is what we're solving for. And then frequency here tells us in the problem that it's 1.5 times 10 to the 13th hertz. Be careful. You do got to watch your units here. Is that the unit we want for frequency? Do we want frequency to be in hertz? Well, yes. We want frequency here to be in hertz, so we're good. So 1.5 times 10 to the 13th hertz. So now we just need to solve for the wavelength here. So if you want to solve for wavelength, all you're going to do is divide both sides by 1.5 times 10 to the 13th hertz. So if I rewrite this for you just this time, you'd have 3 times 10 to the 8th divided by 1.5 times 10 to the 13th, and that would be equal to your wavelength here. So when you plug and chug this and solve, just be very careful when you're plugging this into your calculator because you're dividing by exponents. If you don't have them both in parentheses when you divide, you won't get the correct exponent here. Your answer might look kind of right, but you're not going to have the correct exponent. So make sure you're putting them both in parentheses here. So we're solving for wavelength. As long as your frequency is in hertz, what unit will we spit out for wavelength? Remember, it's a distance here. We're going to spit out meters. Trust me, your units do cancel. Meters per second divided by hertz does come out to be just meters here. You do need to watch your sig figs. We're going to be dividing here, so we're going to count sig figs and use the least. Go back to your problem here and look at the original number of sig figs you had. You only had 2, so your answer is only going to have 2 sig figs. Typically here, we want these answers in scientific notation. So if my answer looks a little weird than what your calculator spit out, make sure it's because, I'm putting it in scientific notation. So the wavelength here when you solve should be equal to 2.0 with correct sig figs times 10 to the minus 5th, and wavelength is going to be meters. As long as your frequency is hertz, wavelength is going to be meters. So that would be the correct answer in scientific notation with sig figs and units. This is the minimum amount of work you need to show. You have to at least show your equation, show plugging in, and then show your answer. And make sure you're circling your final answer here. So just be careful with these problems, watch your units, and obviously sig figs as well. We have one more example here that we can try. This one says, what is the frequency of radiation with a wavelength of 50.0 nanometers? So again, we only have one equation to worry about right now. C equals wavelength times frequency. So that's going to be the equation that we have to use here. We need to figure out what we're solving for. This one is asking us for what is the frequency. So frequency here is going to be that V. So that's what we're going to be solving for. So we plug in what we know. C is always 3 times 10 to the 8th meters per second. Always. You need to know it. Wavelength here, they gave me 50.0 nanometers. Remember, we don't want wavelength in anything but meters for this equation. So you got to watch for that. You need to know wavelength needs to be in meters. So I have to convert here. I have 50.0 nanometers, multiplication symbol conversion line. Whatever unit's on top goes on the bottom, so that's nanometer. I'm trying to get to meters. There is a conversion from nanometers to meters, and you need to know it. There's 10 to the 9th nanometers for every 1 meter. All right, remember, a nanometer is really small, so there's a lot of nanometers for 1 meter. Nanometers on top and bottom, they cancel. So when you plug and chug this, you should get 5 times 10 to the negative 8th meters. All right, remember, the sig figs here don't necessarily matter for this. By taking off the zeros, it doesn't change the number. It's not going to change the problem. Just realize that this number doesn't have the proper sig figs. You're going to base your sig figs on your original problem. So you must be in meters for wavelength. If you're not, you have to convert. You must be in hertz for frequency. If you're not, you have to convert. Another common conversion here you use for frequency is megahertz. So for frequency here, there's 1 megahertz for every 10 to the 6th hertz. All right, so just be careful. That's another common one that you need to know here. So now we're ready to plug our wavelength in. So we got it in 5 times 10 to the negative 8th meters. We want wavelength in meters, and we're solving for the frequency here. So just like before, you're going to divide both sides by 5 times 10 to the minus 8th. You're dividing by exponents, so make sure you're putting both of them in parentheses. Please make sure you're plugging this into your calculator. If you're just watching me get the answer, you're not confirming that you actually know how to do this in your calculator, and usually that leads to problems later on. So when you do solve this with correct sig figs, you should get 6.00 times 10 to the 15th, and you're solving for frequency, so it should be in hertz. As long as your wavelength is in meters, your frequency will spit out hertz. So this is correct sig figs. If you didn't get 10 to the 15th for your exponent, it's probably how you put it in the calculator. Make sure you put both numbers in parentheses when you're doing your work here. So for right now, you only have one equation to worry about. Watch your units, watch your sig figs.